guess I just have to deal with it. I'll put it up there where it doesn't matter. All right. Blake, I'm ready.
Okay, could you do number 57? Yeah, number 57 from this lesson.
Sure. There we go. 57, okay. They asked about this in the other section as well, so I know right away how to do it, which is always great. Okay, it says find an equation of the normal line to the parabola, yada, 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 that is parallel to the line, yada, yada, yada. All right. To write a normal, I'm going to need a slope and a point. Everybody's cool with that? All right. It says that the line that I have to write has to be parallel to this guy. So that's how I'm going to get the slope for my normal line. So the slope for this equation is 1/3. So the slope for my normal line must also be 1/3. Great. Now I need to worry about getting that point from the normal line, or for the normal. Now that point for my normal has to be a point on the parabola, and it has to be a point where the slope at that point is perpendicular to the slope of the normal. So what would that make the slope there? -3. Okay. And I can use that now, because where's the slope of the tangent line coming from? I get it from the derivative. So I can use that slope with the derivative to find the x-coordinate for the point that I need for my normal line. So what do I get here? I get that x is equal to 1. So what this tells me was that the slope, when x is equal to 1, was -3. Right? That's what I just found there. Everybody's cool with that? Now that x that I found, that's where the slope is -1. And the x's don't change between the function and the derivative, right? When we talk about x's, we're talking about the same x's. What does change between them is the y-coordinate, right? The y-coordinate in the derivative is the slope for the original function, and the y-coordinate in the original function is just the y-coordinate for a point, right? So I can use this answer now and plug this into the original. What was the +4? So my normal, the point for my normal is going to be the 0.10. And now I have everything I need. So I can say y minus y1 is equal to m times x minus x1, or y equals 1/3 x minus 1/3. Does that feel okay, Blake? Again, the trickiest piece of this is being able to move back and forth and understanding like what stuff belongs with the derivative and what stuff belongs with the original function. That moving back and forth between them is typically the trickiest part, where you just have to really make sure you understand like what it is that you're doing and what you're solving and what that's going to give me, and how to use like a slope at a point to find the location of that point, right? Which is what we did. We found where on the graph does the function have a slope of -3. And it's at that point 1, 0. That's the only place. Does that feel good? Okay. Everybody happy with my explanations there? That was tried to be really thorough and intentional on how we walk through that. If it's not, stop me and ask some follow-ups or whatever. Totally fine. What's next? Jack.
Number 63, please.
63, okay. Okay, so this says find the second degree polynomial p such that p of 2 equals 5, p prime of 2 is equal to 3, and p double prime of 2 is equal to 2. Okay, when we say a second degree polynomial, what are we really talking about here? We're talking about just like some general quadratic, right? So I need to basically figure out the values for A, B, and C, and then I'll have my quadratic, right? Okay. So it tells me that P of 2 is equal to 5. What that means is I have the equation 5 is equal to A times 2 squared plus B times 2 plus C, or 4A plus 2B plus C is equal to 5. Everybody's cool with that? And maybe I'll call this P of X instead of Y. Okay. Now it gives me some information about the derivative. So I'll go ahead and calculate the derivative. What's the derivative of P of X going to be?
2A.
2AX.
2AX plus BX.
Plus B.
Or B, sorry.
Great. And if I know then that, what did I use over there? Blue. If I know that, that tells me that 3 is going to equal 2 times A times 2 plus B, or really 3 is equal to 4A plus B. And then it tells me about the second derivative. Okay. What's the second derivative going to equal? (2a). So P of 2 then tells me that I have 2 is equal to 2a. Since there's no place to plug the 2 in, right? Okay, well, then I know a is equal to 1. When I step back now, I have 3 is equal to 4 times 1 plus b. So b is equal to -1. And then when I step back to here, I have 5 is equal to 4 minus 2 plus c. So c is equal to 2. I'm sorry, 3. So my quadratic would be y equals x squared minus x plus 3. Everybody cool with that? So the trick, again, I didn't really know how that was going to work out, but I'm like, well, I'm going to just start with the general form. What can I do with this? Not much. I have the derivative, differentiate down. What can I do with this? Not much. I got the second derivative, differentiate down. What can I do with that? That gives me 1. And if I plug back through, I can get, the other coefficients at each step.
I just wasn't sure to start it. So I wasn't sure. I didn't know to start with the quadratic.
Yeah, so like even this
If it
was
says polynomial, should I always just assume?
well, it's the second degree
Oh,
polynomial.
that's right.
Yep, that's how I knew it was quadratic. Yep. Who's next? Blake?
Okay, so for number 67, I just don't really how do we know if that actually creates a corner?
Yeah, let me grab the whole problem here so everybody else can see what we're talking about. Okay. So it asks, is f differentiable at 1? So what we need to do is check to see what the limits of the derivative are in each direction, right? And then it says sketch the graph of f and f prime. Okay. So what's going to be the easiest way to do this? So I guess let's first check that we have, for the differentiable, first thing I would do is check that I have connectivity, right? Is it continuous at 1? Because that's easy to check, right? The limit as x approaches 1 from the left of f of x means I'm going to be plugging into the first equation. And the limit as x approaches 1 from the right means I'll be plugging into the second equation. And f of 1 is also going to just be plugging into the second equation. So we definitely have continuity. So I know that I have that piece. So the only possibility of it not being differentiable is if I have a corner, right? So what I'm going to do is I'm just going to calculate the slope for the left half and the slope for the right half. So let's see, how do I want to do that? How notationally do I want to do that? Maybe we'll do the limit as x approaches a from the left of f of x minus f of a over x minus a. That's the slope from the left. Well, the derivative there is just 2x, right? So it's just going to be like the slope there is 2. Slope from the right, we'd write that the limit as x approaches a from the right of f of x minus f of a all over x minus a. Well, in that case, if I take the derivative of the right-hand side, I get 1. Those aren't agreeing, right? That, to me, screams corner. So, no. If we wanted to graph this, I'm going to graph it on this software because it's a bit easier to graph a piecewise function. So there's the left half. There, oh, I'm dumb. That's not the, that's the half. The left half and the right half. And that's apparently enough of a corner for us to have a problem. Does that feel okay, Blake?
So it's like the instantaneous slopes at 1, they have to match up, right? For it to not to be 1. So even if there's just a slight difference in slope,
yeah,
like that's enough to not be different.
Yeah.
Okay.
Yeah. And in general, when I see a piecewise function like this one that we were looking at, where I have the where one is quadratic and one is linear, I'm very skeptical that's going to work.
Yeah, well, so like the only thing that would work for that is if the linear was like the derivative of it. Right?
Yeah, like if you had something that was like coming down like that, and that was how our piecewise was put together, like that's okay.
Mm-hmm.
But it would have to be like, you have to be picking up with the same slope that the other one is leaving off at.
Yeah.
Which is that's not very often going to be the case.
Okay. Yeah.
So that's really all I'm checking, is to see, is the left hand, once I've guaranteed the connectivity, because they could do something jerky with you, and do like that, where the slopes are going to match up, but they're not connected. So you definitely have to check both.
Yeah.
So I started with the making sure it was continuous, and then wanting to then check the slopes.
Okay.
Mostly because the continuity is easier to check than the slope is. But okay, are these all follow-up questions, guys?
Yeah.
Okay, Teeks.
So in the answer key for the derivative graph,
Oh, we didn't graph the derivative. This is the graph of the function. Do you want to graph the derivative?
No, but I'm just saying, like in the answer key, for the x is greater than or equal to 1, it has an open circle.
It might have just been it's because it's not differentiable there.
Oh, okay.
That's why. That's why. Yep. Good question, right? Because we just explained that it's not differentiable at 1. So when we go to the derivative, you'll have 2x, x less than 1, and then you'll have 1, x greater than 1. We lose that point, that x at 1, because it's not differentiable there, which is what we showed below. Great question. Jack, you had a follow-up on here?
Yeah,
okay.
I'm just clarifying. So for the second part where you took the derivative of, you're taking the derivative of the original function, right?
Yes, I'm just looking at f of x.
Oh, okay. For some reason, my brain thought that you were taking the derivative of the f of x minus f of a over x minus a.
Oh, well, this is just the notation for the slope from the left.
Yeah.
So which is like, I wrote it in words, and then I wrote it symbolically, because this is something that like I can imagine gets slotted into like an AP question, and you have to recognize that that's like all they're talking about would be like slope from the left.
Okay. Yeah, that makes sense.
Which again just like gives me a chance to kind of say it in words, say it with symbols. You don't have to do, you could just use words, would be fine.
Okay, that makes sense.
Which is, I think, what they're kind of expecting at the, now that we have the derivative rules that we have, would not being used. I didn't use that to evaluate the slope. I just used my derivative rules and evaluated at the desired value. Paul.
Can I use the back?
Oh, yeah, of course, dude. Sorry to make you wait.
No.
Anybody else? The earlier ones, though, were pretty easy.
Yeah.
Good. You guys were checking and getting right answers and everything. I'm trying to assign almost all odd ones for that to be the case. I know it's extremely helpful in a course like this to be able to okay, I just did some stuff, I better check.
Yeah.
Okay. All right, well, let's go do some new stuff then. So we're going to continue on with things being mostly symbolic. So today we're going to talk about some more derivative rules. So these two new derivative rules are the product rule and the quotient rule. We'll start with the product rule. And basically what we want to know is how do we take the derivative of something like the product of two functions? If I have the derivative, if I want to take the derivative of some f of x times some g of x, how do I go about doing that? Now, I think the reasonable first guess would be, well, I know that if I have the product or the limit of a product, I can just look at the product of the limits. I mean, could I do the same thing here? I mean, the derivative is based on a limit. And that seems like a reasonable guess. Let's do a little test case then. So let's just say we have our function is equal to x squared. If I take the derivative of that, I get 2x. What if I think about x squared as instead x times x, and I try to do the rule from above? That doesn't work. So nice try. I think it's a normal first guess. So, okay, we made a sensible guess. Didn't really work out. What should we do instead? I'm going to go back to the definition of a derivative. This is the normal route, right? Like we kind of we take a guess as to something that's going to work. We try some test cases and try to see if we can make it not work. If we can get it to work, then we should be able to prove it. Otherwise, we're going to just kind of start with the definition. So I'm going to use capital F here to represent the function f of x times g of x. So if I use my definition of a derivative, that's going to be the limit as h approaches 0 of f of x plus h times g of x, or g of x plus h minus f of x times g of x all over h. Now I'm going to take a look at that and see if there's any clever algebra or some rearranging I might be able to do to kind of break this apart, or I'm not really seeing anything, Mr. Kulik, which probably means the algebraic trick you're going to pull out here is going to be something that's really going to make me groan. It's not so bad. So all I'm going to do is I'm just going to rewrite this as the first term. And then I'm going to subtract off f of x plus h times g of x, but then add it right back. Which we can all agree is okay to do, right? Because I haven't done anything at all. I've just subtracted something, but then added it right back. But what that's going to allow me to do is I can now make some groups and do some sneaky factoring. And you might be asking, Mr. Kulik, why did you choose to add and subtract that particular thing? Well, student, observe what happens when I, from the first term, factor the common factor. Notice that what I'm left with is g of x plus h minus g of x. Everybody agree with that? That looks like part of a derivative definition, right? The derivative, that's part of the derivative of g. That's why I want that. If I do the same thing over here and I factor off my common factor of g of x, what's left? F of x plus h minus f of x also looks like part of a derivative definition. Nice, Mr. Kulik, nice. Okay. So notice that both of these terms have the same common denominator, correct? Everything is all over h, which means that I could write them as two separate fractions over h. Everybody agree with that? And I know that like something times a fraction is the same thing as if I write it in the numerator or if I just write it kind of out front. So I'm going to write this next part like this. So those terms that all have the common denominator h, I'm going to write that just under the second factor. But that's okay, right? Like if I have, 2x over 5, that's the same as 2 over 5 times x, right? Same thing, that's all I'm doing here. But look at what I have in the brackets there. Other than missing a limit, that's the definition for the derivative of g and the derivative of f. Everybody agree? That's the derivative of g. The only thing it's missing is the limit.
Oh, I see.
And that's the derivative of f. The only thing I'm missing is the limit. So what am I going to do? I'm just going to use my limit laws, right? So my limit can distribute to each piece of the factor, and then each term of the expression okay. And what's the limit as h approaches 0 of f of x plus h? F of x, right? And this guy is just my definition for the derivative of g. What's the limit as h approaches 0 of g of x? Just g of x, right? And this was my definition for the derivative of f. So there we go. That's it. That's my formula.
Can you explain how you actually got f of x and g of x?
Well, at this point, I just did direct substitution.
Oh.
So x plus 0 is just x, so I have f of x. And this one, there is no h in there. So g of x is a constant with regard to the limit, so it's just g of x. Is that,
Yep.
That's what you need? Cool beans. This guy's our product rule. Let's do some examples using it. Yeah, Teeks.
Like on the AP test, will they be like prove why the product rule works or something?
I would not suspect they would ask you to do that.
Okay.
But like, should you memorize the formula for the product rule? Oh yeah, absolutely. We're going to use it a ton. We'll use it over and over and over and over and over again. It'll sneak up and get you when you're not expecting it. All right, so let's say that we have the function x times e to the x. Notice that this is the product of two functions. Both of them are in terms of x. Everybody agree? And there's no way to algebraically combine these together that's not like going to still end up with some stupid thing. Right? Like you could make x, you could make it like e to the natural log of x, but then we're going to have like a function composition thing going together when we combine the like terms, and like that's not, we don't know how to deal with that. We will, but not yet. So this we're kind of stuck with, right? There's no sneaky algebra I can do to get away with getting around the product without making something just as problematic for us. Okay, so this seems like as clear of a product rule situation as I could possibly get. So I'm going to have, this would be my f of x. And this I'll treat as like my g of x. So I'm going to have f of x times the derivative of g of x plus g of x times the derivative of f of x. Everybody's cool with what I've written down so far? What's the derivative of e to the x? E to the x. What's the derivative of x? 1. So you could write this as x e to the x plus e to the x. Or if you wanted to, you could write it as like the quantity x plus 1 times e to the x. Either is okay. Does everybody feel okay with that? What if I wanted to say take the second derivative here? Does it matter which version of the answer the first derivative we use? No. Which one do you want to use? They both would have product rules in it. Right? The first one has the x e to x in it.
But then I think like the product rule would probably be easier on the second, right?
Yeah. I think it kind of is also. So let's do that. We tried it the other way first, or with fifth period, and I didn't like what happened. So we'll do it this way this time. Oops. So we have f of x times the derivative of g of x plus g of x times the derivative of f of x. Now here I'm writing out like the product rule before I take derivatives of things. if you get comfortable doing this, you can just like skip this step that I'm doing right now and just write out the product rule where you've done the derivative. But if things are getting complicated, often it's nice to like not do that, to include the work. It's a little bit easier to not get out of, or things out of hand. So again, the derivative of e to the x is e to the x. The derivative of x plus 1 is? No, just 1. And so you could write your answer as, if you distributed things out and combined like terms, you'd end up with x e to the x plus 2 e to the x. Or in the factored form, you could write it x plus 2 e to the x. Hey, Mr. Kulik, starting to sense a pattern here. Yeah, so what if I want the 100th derivative of f of x? What do you suspect that's going to be? Just quick in your head. X plus 100 e to the x? Yup! Not uncommon when we have that exponential rattling around in there, is that you just keep accumulating stuff as you go and take derivatives. It's one of the rare occasions where the derivative is getting actually more complicated. As you take more derivatives, it's getting worse. As opposed to, like, if you have a polynomial, every time you take the derivative, it gets simpler. Well, Mr. Gulick, that's yippee. But hey, guys, we did it. It's no big deal. All right, let's do another example. Let's say that we have this function. So we have the quantity a plus bt all times the square root of t. How do you want to do this? Anybody got any suggestions? Oh, yeah, I mean, okay, we could do the product rule. I shouldn't say try, we could absolutely do that. So that's okay. But I would argue there was a simpler way of going about doing this. Yeah, so remember that the square root of t is just t to the 1/2. So if I do that and just distribute things through, I get that. And shoot, if I think about it that way, that's something I can just do in my head, right? A over 2 t to the -1/2 plus 3b over 2 t to the 1/2. The point of this example is just because you have this new hammer, every problem doesn't have to be a nail, right? There's a situation where a little bit of distributing got you out of having to do a product rule, which ideally this kind of thing becomes second nature, looking for ways to make the calculus easier by doing some algebra. So again, if you have the opportunity to FOIL or to distribute or something like this to like make the problem simpler to get around having to do a product rule, oftentimes that's helpful. Now this example, it wasn't really bad either way. You'd end up with the same thing, but you have more cleanup to do after the product rule for sure. You have more combining of like terms that you'd have to sift through and all that nonsense to end up with the same thing that we have over here that we should have gotten pretty easily, right? That was an easy derivative to do. So that's the point of this example, was to just illustrate to you that, like, if you don't have to use the product rule, maybe don't do the product rule. Like, just do just some algebra. Let's say that we have this situation. So let's say we have the function f of x equals g of x times the square root of x. And we're told g of 4 is 2, g prime of 4 is 3, and we're asked to find f prime of 4. Well, it stands to reason I'm going to want to calculate the derivative here for f of x in general, and then just plug in the 4 at the end, right? Pretty clear-cut case of this being a product rule situation, where I have two functions clearly multiplied together. Since g of x is just written abstractly, there's no combining of like terms that I can do here. So I'll have f times the derivative, the second function times the derivative of the first plus the first function times the derivative of the second. I shouldn't say f and g's there because, well, g of x was the first function I wrote, and then that was going to get confusing. The derivative of g of x is just going to be g prime of x. The derivative of the square root of x, I'm going to think about the square root of x as x to 1/2. Is everybody cool with what I've done so far? I thought of the square root of x as x to 1/2, and then I just did the power property, or the power rule, I should say. I keep wanting to call them properties. They're not properties, Mr. Kulik. Properties are your exponent rules. Okay. Well, now that I have that, I can just do f prime of 4. Now, notice I'm not going to do any cleanup there. Why am I not going to bother cleaning that thing up at all? Because the problem just asks for me to plug 4 in, right? I don't need a simple expression to do that. Like, why give the possibility of making some stupid algebra mistake, cleaning things up, when all I really have to do is plug 4 into my answer. It's not asking me for like a simplified expression. It's asking me for a number, right? So I just do that. You know what I mean, guys? Well, the square root of 4 is 2. I know g prime of 4 is 3. And then I know g of 4 is 2. And then 1/2 times 4 to the negative 1/2. Well, what's 4 to the positive 1/2? 2. Great. So 4 to the negative 1/2 should be 1/2, right? Because they're making a reciprocal from the negative exponent. So I have 1/2 times 1/2, so that's 1/4. So 6 plus 1/2 is 6.5. Jillian.
Where did the 1/2, the 1/2 come from? Like in the first place, where
That's the same thing as the square root. Right,
so
the
you're
square root.
saying just that specific root x equals just the 1/2, not the entire.
Correct.
expression.
Yeah,
Okay,
yeah,
I
yeah,
see.
yeah.
Okay.
Yep. I'm just saying that's what I'm thinking about when I'm doing the derivative, was that those mean the same thing. Jack.
Sorry, can you just explain the 4 to the negative 1/2? What's that?
Yeah, so it's like 4 to the negative 1/2 is like 1 over 4 to the half,
Oh, so okay, thank you.
right? No problem. I just want to point out too that on occasions, depending on how many products you have together, you may have like product rules inside of other product rules. So say for the example, you have the product of 3 expressions. Now we don't have 3 different things that we know how to take the derivative of that we can't just turn into polynomials and like combine some like terms to get around having to do something like this. So I'm not going to do a specific example, but I'm just going to do it with F, G, and H to give you an idea of what's going on here. So I'm just going to think about one of these or a pair of these as just one thing. Okay? So I'm going to think about this is a product rule where I'm going to just, those are my 2 functions. So the second function times the derivative of the first function plus the first function times the derivative of the second function. Everybody's cool there? Notice here, that's another product rule. So I have like a product rule inside of a product rule. Or if I just wanted to simplify this down, so if you had 4 or 5 or 6 or 12 products, it all kind of just does the same thing. Notice the pattern where you have one derivative and the other 2 that not derivative versions. And since they're all being added, does it really matter the order that you're doing any of this stuff? As far as the formula goes? Nah. Do we feel okay doing this? A lot of just symbol pushing, right? Nothing theoretical here. Should feel pretty comfortable. We're just doing, like symbol manipulations, which we have a lot of practice at in our mathematics career. The conceptual stuff is usually harder at this level because we just don't get as much practice like thinking about what these things mean or what mathematical ideas mean in relation to one another as much as we do just like pushing symbols around. But this is, like 80% of this first 5 sections is just symbol pushings. So enjoy, right? So what if we want to talk about the quotient properties here? I'm not going to do the proof for this one because, I don't know, it's almost a full sheet of my notes, and I don't think we gain that much by doing them, so I'm just going to quote the property here. I don't mind doing some of them, but it's always like a balancing act between getting everything done and like doing everything to like the most rigorous way possible. Sometimes it's just worth quoting the property when the proof is going to be a little bit tedious to get to. And not that the proof here is ridiculous, but it's more or less the same idea that we did before in the product property. I think given a little bit of guidance, it wouldn't be tough for you to get to the same spot. But let's just not. And we'll just have more time then to do examples of things, which I think is probably what we're thirstier for than like another proof of something that all you're really ever going to have to do is use the formula on. You know what I mean, guys? All right. While I want to do some of the proofs, we're not going to do all the proofs. Because it just, something's got to, you have to make sacrifices in life. Okay, so clearly a product, right? In addition, there's no way to write this so it's not going to be a product because it's a polynomial on the bottom, not a monomial. I can't just like break it up as a bunch of common denominators and do some clever reducing or whatever. And if you look at this, the denominator doesn't factor without, or at least over the rational numbers. Like you can use a radical or whatever and use a sum of cubes to do that, but like I'm not gonna be able to reduce anything by doing that, so like why would I bother? So it's like textbook quotient property problem. So the quotient property is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Notice here, because of the subtraction symbol, the order matters, so we have to make sure that we're doing the correct order. And all of that's over the denominator squared. Now, a word of wisdom here. What we're going to do is we're going to do the derivatives and then try to simplify this as much as we can. Is there any reason that I'd want to do anything to that denominator? No. Because if there's ever a chance that I'm going to be able to do some reducing, that denominator's got to be in factored form anyways to do that. So unless there's like some obvious thing that I can cancel and simplify, like if I had the square root of x cubed plus 6 squared, sure, let's do that and cancel the square root with the square root or something. But if it's just like a polynomial down there, I'm never going to touch that thing. Everybody's cool? And the only time I would ever even consider it is if it's like I have a multiple choice question and all of the answers in the multiple choice have like foiled out denominators. It's like, all right, well, I better FOIL this out just to make sure. But come on, people. That's probably not going to be the situation. Okay. So let's do some derivatives here. What's the derivative of x squared plus x minus 2? 2x plus 1. And then the derivative of x cubed plus 6. 3x squared. Okay. I guess what we'll do now is going to FOIL the first pair out and then distribute the second pair. Everybody's cool with that? I don't. FOIL. Distribute. That's all. I don't think there's anything clever that I can do to get around having to do this the hard way. Do be careful with your negative sign there. Notice the negative sign in front of the stuff in green. So I have to distribute that negative sign through when I distribute the 3x squared through. That's why all the signs are flipping on you. Oops. Squared. Yep, did I forget it up there too? Same thing. Good job paying attention, guys. All right, then let's just combine some like terms. Let's see here. Those guys will go together, give me negative x to the fourth. And then these guys will go together. That'll give me a negative 2x cubed. I have only one x squared term, one x term, and one linear constant term. So that'll all go together like that. Now I'm going to take a cursory glance at the numerator to see if there's any factoring I can do. But right away I notice that's a 5-term polynomial. I don't have a good way of factoring any of those unless it's something like super obvious, like there's a greatest common factor or something in there, which there's not even one of those. So I'm not messing with this anymore. I'm pretty confident that this would be as reduced as I could possibly get. Now, if the numerator was like a quadratic or something where it was a little bit, or is in the quadratic form where it's like, oh, okay, maybe I can like factor and reduce a little bit here. Maybe I'd monkey around with it a little bit more, but with 5 terms, like, probably ain't anything I can do with this. Particularly for just like a normal, ordinary numeric problem. If it's like some proof thing, it's like, okay, if I know where I'm going to and I know there has to be some reducing I can do in here, then let's keep going and see if I can play with this a little bit. But
Wait, so how do you know if you're like completely done?
well, I just looked at the numerator to see if I could factor that at all. It's a 5-term polynomial. Like the only way we had to factor that was doing like looking at the graph, finding the x-intercepts, and trying to do the synthetic division nonsense. Like, we're not doing all that.
Right.
There's nothing obvious that I can do with that numerator, so I'm just stopping. If it was like in the quadratic form where maybe I could factor it, and then maybe there's some reducing I could do, yes, I would continue to play with that and see if there was anything good I could do there. But I would say the vast majority of cases, there's going to be nothing to do after you've like multiplied things out and combined like terms in the numerator. Majority of the situations, there's going to be nothing really to do. All right, let's do one more example. Oh, excuse me. Or 2 more examples, and we'll be done here. Okay. All right, so let's say I want to write the tangent line to the curve y equals e to the x all over 1 plus x squared at the point 1 comma e over 2. So to write a tangent line, what do I need? Yeah, I need the slope and I need a point. Well, the point we have, and what that tells me is really the place where I want the slope at, right? I need the slope at x equals 1. Where am I going to get that from? Yeah. So that's just going to be the derivative evaluated where x equals 1. Okay. Well, let's get after it then. Get going on the derivative because that's the only piece that I need. Okay, it is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay. So go ahead and do those derivatives. The derivative of e to the x is e to the x. The derivative of 1 plus x squared is 2x. So there's that. Now I'm not going to bother to clean this up. Why aren't I going to simplify this? Because all I'm going to do with it is just plug x equals 1 into it. Am I good to plug x equals 1 in right now? Yeah. Is simplifying it going to make plugging it in any easier? Not really. Is there a chance that I make some dumb algebra mistake and goof this all up? Yeah. Much better chance of that happening than making it, the plugging in any easier. So I'm not bothering to try to simplify that anymore. So what do I get here? I get 2e minus 2e over 4. Oh. That's 0. So the slope is 0. Oh, what does that mean? What kind of line has a slope 0? Horizontal. So what do I need to write the slope of the horizontal line? Just the y-coordinate that it has to pass through, which is what I have here. And I'm done. Yeah, that ain't bad, right? All right. One more example. What do I do with this one? Work smarter, not harder. No, man. We're just going to do this. Since that denominator is a monomial, I can just rewrite this one fraction as two fractions with a common denominator. And do I need a quotient property on that? Nope. Boy, that seems like a good darn doggone deal. Which is quite a bit nicer than grinding through the quotient property, because that was going to be, there's going to be some weird reducing and who knows what else that had to happen on that. Again, my caution to you, just because you have a new hammer doesn't mean every problem is a nail, right? So just because you could use the quotient property or the product property doesn't mean you should. Oftentimes there may be some algebraic way to get around doing it. Now, would it have been okay to use the quotient property still here? Sure, but in a timed AP test, if they do it the way that takes like an extra 3 minutes, like that's 3 minutes, or versus the way that took 30 seconds, that's like 3 minutes that you've sacrificed to do something else that maybe couldn't have been, like there's no quick way to do it. It just you need time. Anise?
So like when you see square root of x in one of these problems,
all I'm looking at is the denominator. Okay. I want that denominator to be a monomial. If it's a monomial, I can do that trick I've just done. Right. If it's a polynomial, I can't. I'm stuck doing a quotient property. Okay. So it's not the square root that told me there's a shortcut here. In this one, it was there was a monomial in the denominator. Is that?
Yeah, and then once you do that, then you can use a little trick.
Yeah.
Okay.
Then I can just reduce and it's a power rule problem instead of a quotient rule. That's a big help. All right, that's it for this section. So again, nothing hugely theoretical, just kind of getting used to the new rules and pushing some symbols. The problems here for this section, similar to the problems in 3.1, in that they're mostly symbol pushing, a little bit of like, you know, like tangent line, normal line kind of stuff maybe at the end, but nothing too bad. Now these new rules that we just got, the quotient and product, have to have them memorized. Okay, the AP will expect to have them memorized. In fact, all these fancy derivative rules we're going to talk about this chapter, you need to have memorized. At this point on the top of page 189 has a little red box that consolidates all the derivative rules through section 3.2 all in one place. So if you're a flashcards or Quizlet person, you want to make one, that's got a comprehensive list of all the derivative shortcuts that we've seen in chapter 3 up through section 3.2 is at the top of page 189. But I would get on that sooner rather than later to make sure that you have those down and you can use those, because they do not go away. They pop up sometimes when you least expect it. So it's something we have to be really careful about, and you're going to want to get that memorization started kind of early. The other thing I wanted to remind you guys is that we're going to split chapter 3 into 2 parts. So we're going to do the first 6 sections and then do a test, and do the last 4 sections and do a test. The first 3 sections are largely symbol pushing. And then the last 4 sections are like application. So we're going to be using like these tools on like real world situations. In particular, 3.9, that situation tends to be rather difficult for students, not because the calculus is hard, but like understanding what's going on and how to think about a story problem in a calculus way is hard for students in the beginning. So we'll spend more than one day doing I'll do some examples from 3.9, and then you guys will have a day where you can just work together on some examples from 3.9. Where you can ask me questions and stuff. So that'll be coming. I would like to, what do we have, 2 days next week? I'd like to do 3 sections probably next week in chapter 3. Then 3.3 is pretty light section, where there's not a ton going on. So I think I can probably do 3 sections next week, but that means we're probably looking at the first part of the chapter 3 test the week after. The plan on that would be I'm probably going to weight these so that in total both chapter 3 tests is like 100 points total, so that it's not like chapter 3 all of a sudden is worth twice as much as chapter 2 test was. So it'll be like a 50-50 or 60-40 or something kind of ish like that, just to give you guys a heads up. Everybody cool? Okay. All right, I'm done here for today. For Sunday's homework check, we're only looking for section 3.1. So 3.2 goes on to next week's along with at least 3.3, and we'll see past that what we're able to get through. Okay?